uh, just to sensitize you, you already know this, but to sensitize you about the differences between theory and practice. Right? In theory, things work fine. In the lab, when you get, often, there are surprises that are there in the lab. So an example of, from 380 lab itself, about the difference between the two. So this has to do with actually experiment number 3, not the experiment number 2, but is pertinent to our discussion, so I've brought it here. So this is a BJT, and somebody was trying to measure the gain of a bipolar transistor, right? And the person was trying to measure the gain of a bipolar transistor because that person was building a common emitter amplifier. This circuit should be familiar to you, right? This is a common way of biasing. So the idea was, can I measure beta of a transistor in the following way, right? So method 1. So the idea in method 1 is, you note that you take this particular circuit and you find out the values of the base voltage, the collector voltage, and the emitter voltage, right? So what I'm trying to do is illustrate to you the difference between theory and experiment. So in theory, instead of actually working out on paper and pen, I'm going to use simulator. Simulator is also a theoretical calculation. It's not a measurement in the lab, right? So simulation is also theoretical. So I'm showing you this particular circuit, and if you simulate the circuit, I'm telling you what the beta is, because in the simulator, I've put a value of beta equal to 200. All right? So in method 1, the idea is that you measure the base voltage, you measure the emitter voltage, and you measure the collector voltage, right? So these voltages are all given to you. And then the idea is you calculate IC. IC is 5 minus this voltage divided by RC. So that's IC here. Emitter current is emitter voltage divided by RE, which is 1K, so that you get the emitter current here. And then you are trying to measure beta. So what you do is you calculate base current, IE minus IC, so you get 5.144, and then you take the ratio of IC and IB, and you get 198.77, right? So in theory, the method works fine. You get, if I had taken more decimal places, I would have gotten it almost like a perfect answer, right? So we get 198.77, beta is 200, the method seems to work fine. That's method number 1. Let me show you method number 2. Another student says, well, I don't want to measure it in this way. I want to measure it in a different way. And this person says, method 2, that I'm going to calculate this current. So this current will be 5 minus whatever is the base voltage divided by the resistor here, 82K. So I will calculate this current I1. Then I will calculate this current I2. Right? So I2 is 1.6695, 47K, 35, whatever, I'll calculate this, I2. And then I will take the difference between I1 and I2, and I'll calculate the base current. Right? I'll calculate the base current here. So base current comes out to be here. Then I know the collector current, 5 minus 2.2 divided by RC's collector current. I'll take the ratio, and I get beta, which is 200.715. So this is also very close to the correct value. 200 is the ideal value, so this is very close. So method seems to work fine. Right? Both methods are working fine. Method 1, method 2. Method 3, this person says, why are you making all this complicated circuit? Make a simpler circuit. Make a simpler circuit here, apply some voltage here, and measure the, so you measure voltage here, measure the voltage here, measure the voltage here, and calculate. So IB equal to VBB minus VBE by RB. That's the base current. And collector current is VCC minus V out by RC here, and calculate the beta by taking the ratio of IC and IB here. Right? So as an example, you apply 2.5, you get 2.13 here, you get 0.669 base voltage here, you calculate beta equal to 201.88. All three methods seem to be working fine, right? So this is here. So in theory, method 1, method 2, method 3, they all seem to be giving you all, as expected, all right answers. Or as I said, the errors are mostly because of some number of significant digits that we have taken. So you get all right answers here. Method 1, method 2, method 3, they're all the same in theory, right? So now get into the lab and apply each one of those methods and see what happens. So this is what was done. So in experiment, a transistor BC547 was taken, this circuit was built. Don't worry about these AC sources. We are not talking about AC here. No AC was applied, so all these things are not there. So note the value. The value here is 1.644. This was measured, 2.104, 1.058. This was not exactly 5. It's about 6 millivolt higher than that, 5.006. So you're seeing that we are measuring up to third decimal place. That was the capability of the instrument that we were using for measuring. So we measured all these voltages, right? So let's apply method 1. All right, so obviously, first of all, note that there is a difference between simulation and experiment. Simulation was telling you 2.239, here is 2.104, here is 1.058, here is 1.028. And that we expect, differences we expect, because in simulation, beta is 200. Here, I don't know the value of beta. Beta could be 300, beta could be something else. All right, so the transistor here it will obviously be a little different from the transistor that I've simulated. Beta may be different and other things also may be different, all right. Okay, anyway, so let's apply the 3 methods. Method 1 was calculate the collector current, calculate the emitter current, take the difference of the 2 emitter and collector current, calculate the base current, take the ratio, calculate beta. So let's do that. IC is 5.006 minus 2.104, 2.7K, 1.075. IE is 1.058 by 1K. So we get this. We take the difference. We get minus. We take the ratio. We get a negative current gain, minus 63.9. I'll come to that, okay, later on. Why? And so we get a negative, which is obviously wrong. The method is not working. Okay, let's go to method 2. So method 2 was calculate this current, take the difference, calculate the base current, and then take the ratio. So I1, 41 microamperes. I2, take this here, 34.98. Take the difference, 6.02, 178.5. Right? So the previous one gave minus answer, this one gave 178.5. Let's apply method 3. Method 3 was this circuit here. We applied 2.504 here. We applied 2.5, but measured voltage was 2.504. This is 0.668. This is 1.405. And we calculate base current and collector current, take the ratio. We get 252.6. All right? So in experiment, method 1, minus 63.9. Method 2, 178.5. Method 3, 252.6. In theory, all 3 methods were working equally well. In practice, when you go to the lab, all 3 methods giving you widely different values. Widely different. One is even giving minus value here. Widely different values here in experiment, in practice, right? So this is very troubling. Why is it minus? Beta is not a minus. Why is it minus? So one of the reasons why things don't work properly in the lab is, or according to expectations, are that there are always errors in the lab. Whatever you measure has an error in it. In theory, you're doing a perfect 4th order, a 4th decimal, 5th decimal, whatever you want. You're doing almost like a perfect calculation. In lab, the measurement always has errors. In this case, one obvious error was, well, I've written here 82K. The resistors that you take in the lab is written 82K, but they're never 82K. All resistors have a tolerance. So if you take, in the lab, if you pick up a 1K resistor, and if you had a very accurate meter for measuring the value of the resistor, you will find the resistor is 1K, 1.01K, 1.02K, 0.97. It's varying. It varies, you know, it's got a normal distribution with some standard deviation and all that. So the resistors are varying, so we said, okay, let's not use the value that is written on the resistor code, right, 2.7 and all that. Let's actually use a multimeter and measure the values here. So we did that. So the actual value, instead of 82, I'm not saying this is the most accurate, 82.7. This came out to be 47.1. This came out to be 0.976. This was 2.72, different from the values here. Now I apply method 1, I get a gain of 62.37. It's no longer negative, because at least I've tried to reduce one of the sources of error, which was I didn't take the value as it was. It is a measured value, but the measured value will also have errors in it. It's not going to be 82.7. It may be 82.73 or 4. We don't know. The multimeter didn't have enough accuracy to give me a second and a third or a four-digit value of this particular one, right? So these will have errors in it. Similarly, all the voltages that I measured will have errors in it. They will all have errors in it here. So method 1 gives, method 2 also gave a little different here, 185.6. So let me summarize. The 3 methods in experiment gave now 62.37, 185.6, and 252.6. Right? So which one will you pick? All are obviously not right, but which one will you pick as the right value? The first one, that looks too low, right? It may not be correct, but that's not why. I don't want you to guess, but have some reason for choosing one or the other. So, theory, all 3 are working fine. Method 1, method 2, method 3, but in the lab, quite different. Right, so this also illustrates that you may take a circuit and simulate it and find, oh, everything is fine. You come to the lab, things are not working fine. Right, so which one would you prefer? Can you see some obvious problem with the measurement associated with method 1 and method 2? Both techniques have a very, very important flaw in it as a measurement technique. Huh? More resistors is not an issue, not that much. Huh? So we are measuring the voltage, right? We are measuring, see here also we measured this voltage, 3 voltages we measure. Here also we measure this voltage, and this voltage. And the same instrument is being used for measuring all 3. There's no different instrument. Exactly same instrument with the same precision. These were measured. In fact, the values that I'm giving you, these values, I measured it by actually taking a circuit. So we didn't rely on different students measuring different things. So I measured using all 3, right? With the same circuit, same instruments, everything same at the same time, almost at the same time. So the problem that you see here, in theory, all 3 methods are fine. In experiment, all the 3 methods give you very different values here. And there's a problem with method 1 and method 2. And the major problem with method 1 and method 2 is, as somebody said, look at the way the current is being measured. Look at the way IB is being measured. So beta is IC by IB. So IB is the difference between IE and IC. Difference between IE and IC. And the 2 currents, IE and IC, are very close to each other. The 2 currents, you know, emitter current and collector current, are very close to each other. So any error here, any error in measurement of emitter current or collector current is going to cause a big error in IB. Similarly, IB here is a difference between I1 and I2. In a properly designed amplifier like this, I1 is very close to I2 again. So I1 and I2 are also very close to each other. So any error in the measurement of I1 and I2 will also cause a very significant error in IB. So IB here in these 2 methods is highly error prone. While here, if you look at IB, so you're saying, well, in this case you're taking a difference, in this case also you're taking a difference, here also you're taking a difference, but there's a difference between the 2. The thing is, here VBB was what? 2.5, and this one was about 0.7. The 2 values are not close to each other. VBB and VBE are not close to each other. They're fairly far apart. Similarly, VCC and Vout are also not close to each other. It's 5 here and the value here is, let's say, 2.5. They're far from each other. So this is not so sensitive to errors. Let me explain with a very simple example here. Say you are measuring or estimating Z, which is the difference of two measured quantities x and y. Right? You are experimentally measuring x, you are experimentally measuring y, and you're calculating Z as the difference between x and y. Obviously, when you're experimentally measuring x, there would be an error in it. Similarly, there would be an error in y. So let's do that. Delta Z will be equal to delta x plus delta y. Errors can be positive or negative, so we'll add them up. Let's calculate the percentage error. Delta Z by Z is percentage error. So that would be equal to delta x by x multiplied by x, delta y by y multiplied by y, x minus y. All right? That's a percentage error. Let's assume that the percentage error in x and y are the same. Whatever it is, 1%, 2% or whatever. Let's say the percentage error in both the same, then I can simplify it and write delta Z by Z. The error in Z is error in x multiplied by x plus y divided by x minus y. All right, so now if you do this calculation, so this is the error in the quantity that you're estimating. Let's say this is the base current. Z is the base current. This is the emitter current. This is the collector current. Right? So let's say this is 101 and this is 100. 101 and 100 here. Right? Two values which are very close to each other. What does this factor become? 201. What does it mean? Percentage error in Z is percentage error in any of these quantities x and y multiplied by 200. So 1% error in x or y will get multiplied by 200, will give you 200% error. Percentage error in Z is 200% if the percentage error in x and y are, I'm talking about percentage error, is 1%. What this is telling you is never estimate anything in the lab which is a difference of two very close quantities. Never try that. If you do that, you are in big trouble here. Your Z can have lots of error in it, and it's not a reliable estimate. Now, instead of 101 and 100, suppose I took 100 here and 50 here. The two are far apart. You can easily do all this calculation. You'll find that the errors are much smaller. So in lab, you cannot avoid taking difference of two quantities. But when you take a difference, make sure that the two quantities are very close to each other. If two quantities are far from each other. If they're very close to each other, you can be in big trouble, that is there. So in theory, all three methods are fine. This one, and this one, all three are fine. In practice, method 1 and method 2 are highly sensitive to errors and will give you incorrect results. Never use them. Don't use them. Use this particular method here. This is far more reliable. So the value that I got is 252.6 here. This is far less sensitive to errors. I would believe this and will say beta is around 252. Beta value is 252. Okay? All right.